Okay. All right. So now I think um did you learn anything about like the bonds and the valence electrons of carbon, right? You probably learned that every carbon or every atom prefers to have 8 electrons in its octet, right? And that's like the
Yeah.
octet rule. So carbon also prefers to have 8 electrons in its octet, and when the octet is complete, so it would then actually have um four, 4 bonds, right? When it has 8 electrons in its octet, it would actually have 4 bonds, 1, 2, 3, 4, right? So um, every carbon will actually form 4 bonds, and when it's not 4 bonds, then either it'll be a positive charge or actually just like a negative charge. So, okay, now if you go from here to actually drawing out the bond line structure, so then in organic chemistry, because you already see how there are like a ton of hydrogens here, right? And because there are a ton of hydrogens in organic chemistry, they do not like to write hydrogens. And then also the other thing is that what if we think about the hybridization of this carbon, right? So what is the hybridization of this carbon at that?
S
Well,
SP3.
that's right. So it is an sp3 carbon. And if you think about the geometry, right, of that carbon, sp3 hybridized carbon is tetrahedral,
Tetrahedral.
right?
Yeah.
So then when we go from like this structure, which is an expanded structure, to a bond aligned structure, then when we're converting every atom to a bond. So how we write that as is we would just write, right? A carbon is actually just like a dot. We don't even write the hydrogens. We don't write hydrogens. And then, so carbon is when it's getting connected to another carbon, then we've got another kind of a dot. So then that line is just representing carbon connecting to a carbon, and then we don't write carbon as well. We don't even represent any hydrogens, right? And then we have 1, 2, 3, 4, 4, and then 5. So we actually have 5 in the straight chain, right? 1, 2, 3, 1, 2, 3, 4, 5. And then what we also see is, and then again, they're all tetrahedral here, right? So it's actually they're all zigzagged. And the reason for that is that this is representing a tetrahedral geometry. So how does that work, right? So if you think about, let's say this carbon over here, like this carbon over here, right? So there's a hydrogen here and a hydrogen here. So now if you think about the geometry for this carbon, actually every carbon, right? It is the angle over here is 109.5, which is representing the tetrahedral geometry, or the 109.5, 109.5, 109.5. And then to be able to maintain the tetrahedral geometry at every carbon, then they show up as zigzagged bonds to kind of maintain that geometry at every carbon. Okay. And then we don't write the hydrogen, so we're not going to write it here. So we're just gonna eliminate them from here. Okay. Now, if you think about C2, right? C2 is also connected to a CH3 over here, right? So this CH2 also is connected to the CH3, so that would just be represented by another carbon over here, just like that. Okay, and then C4 is also just represented by a CH3. Okay, so C4 is also connected to a CH3, 1, 2, 3, 4, and on top, it also has a CH3 at the bottom as well, actually, right? So then, meaning that there are 2 CH3s connected to it. So then we can just represent that as 2 bonds here, because they would now make for the tetrahedral geometry at this carbon. So straightforward, right? So not that hard. So let's are you able to draw
Yeah.
out on my screen? Are you able to draw the structure for the second one in the box?
Uh, no, but I think so. We already like started doing OChem. Uh,
Mm.
like so we covered up to acid base. I think
Oh, you
because like with you
did
whenever
we?
we had yeah because
Did
we
we
had
did?
extra classes. Yeah, so
Oh,
that's why I thought like I saw the worksheets. I was like, oh,
oh,
this
okay.
must be
I
from
totally forgot
where
actually.
we yeah.
I
So
see. I
so
see. I see.
basically
Okay. So
yeah.
do we do this? Can
So
you do
yeah.
this then? Okay, let's see. And then
Yeah.
maybe we'll review formal charges and then maybe we'll move on from there.
Yeah, so we can like go a little bit quicker if we,
Yeah,
yeah.
yeah. Let's
So
do that actually. Yeah.
how do I draw?
So I think you should get an option to annotate. So maybe like you see like three dots, and then
Yeah,
when you
more.
click on them, yeah, maybe, and then see if
It says whiteboards.
not that one. It should just say annotate. Or
Yeah,
do
it
you
doesn't
see
say
any
that.
pen floating around anywhere else? No
No.
pen floating around. Where does it say tools or anything else? Maybe on top. Is there any tab on top which has three dots or something?
No. But I mean, I can just tell you what quickly what to
Okay,
do.
sure. Let's do that. Yeah.
Yeah, so you can just draw the. Mm, it doesn't matter how we orient it, but
Hmm.
I guess you could draw the carbons horizontal first. Uh, we can start that as like the main
Yeah,
chain because they're
right.
the same length, so it
That's
doesn't
right.
matter.
Yeah.
So yeah, you can start like down. So the very first carbon will be down. The
Okay, I like that. Let's see. Oh,
yeah.
okay. Hmm.
Okay, and then you can go draw carbon 3 and carbon 4.
Okay, so we got 1, 2. Okay, so 3 and 4. Let's say 3 and 4. Okay.
Yeah. And then carbon 3, you have to draw the oxygen because it's not a hydrogen. So you have to
Right.
draw
Okay.
double bond and then the
Okay.
oxygen.
Okay.
And then yeah, that's it.
Okay. Right. So
Yeah.
we got this, and then do we have anything else? So we got 1, 2, 3, 4, right? And then, so have you
And
accounted
then
for
the
all the carbons? Yeah.
fifth carbon, yeah, up there.
Yeah. So that's connected
Yeah.
to,
Carbon 2.
that's right. So that, where would that go?
Right, yeah, right at the node. At the node, you can just draw one
Right.
line up. Yeah,
Yeah, like that, right? Okay, great,
yeah,
perfect.
yeah.
Nice. Okay, so that was that. And then actually, let's actually do 1.24.
2, 4. Okay. Okay. So yeah. So this one you can again just draw the carbons. Like you can. It looks like we can change the axis and just draw it horizontal to
Right.
make it easier.
Yeah, sure.
Yeah. So then it will be 3 carbons. So one,
Okay,
2, and then yeah, just
right.
like that. Yeah.
Yeah, yes.
So then attached to each carbon, there's a OH, a
Yeah,
functional group.
right.
So
Okay, yeah.
so yeah, we can just
Right. And then
yeah,
on 2, we have an OH, and on 3, we've got an OH as well.
yeah.
Okay, perfect. Okay. So I don't know if we did this or not because I might have just missed this one because I saw this problem and I thought it's interesting because we have not really I haven't really done this
Yeah.
type of a problem with my students before. So in this problem, right? So they're already giving us a transformation reaction that's happening, and then we
Mhm.
have to predict it either or whether it's actually an elimination reaction or actually a substitution reaction, right? Is that the
Yeah.
only two possible? I think there's this okay,
There can be
addition,
both, right?
addition.
Yeah.
Probably not actually. So it'll either be addition actually or an elimination or a substitution.
Okay.
Um, right. So what are you thinking? You're thinking it can be addition or elimination and substitution both?
Yeah, a combination. But
Okay, so if in one reaction two different transformations are happening, then yes. But I think in this one they'll only most likely do one at a
yeah.
time,
So
right?
yeah, the
So
first one is
yeah,
probably a substitution.
yes, that's right. So this is actually a substitution reaction that we will learn about, right?
Yeah,
And
that's
then
what I was about to think.
yes,
Yeah.
exactly.
Addition.
That's correct. This is the addition reaction. Okay, next
Yeah.
one.
And the last one just elimination.
Right, and what is actually getting eliminated?
The chlorine.
That's it.
And then
Yeah.
yeah. But then it forms the double bond to
Right.
stabilize the charge, right? Or
Right. Okay. If you think about it,
uh,
how many hydrogens at this carbon right now, as represented in that
uh,
structure?
one,
Right. One, two, three, four. And how many were here?
zero.
Right. Exactly. So hydrogen is eliminated as well then.
Yeah, with the chlorine to
Right.
maintain charge.
Right. Plus HCl.
Okay,
Yes. Exactly. And that's why then there
okay,
is a double bond. Right.
yeah,
Yeah.
okay.
All right. What about this one?
Wait, have we? I don't like like are isn't substitution reactions like its own unit like later on?
Yes, it is. And elimination as well, and addition as well. They all are.
Oh, okay, okay,
Yeah, I think it's just identification right now.
okay, okay, okay,
Yeah,
okay. Addition for
that's correct. It
128.
is. Yes.
Okay.
What about the next one?
Mm, elimination because you're gonna lose the hydrogens and you're gonna
Right.
form double
Yeah.
bond.
Yes.
Yeah.
More like an
Okay.
elimination.
Yeah. Okay. And then this is substitution.
That's correct. Yeah.
Okay.
Okay, what about the
And
next
then the
one?
last one is again, it's just like 129. Now you're forming a triple bond, so
Right.
elimination.
Elimination, that's correct.
Yeah.
Okay, perfect. Um,
Yeah.
okay, what is this then?
This one will be the reverse, which is addition.
That's right. This is more like an addition reaction. And what
Yeah.
is getting added actually, if you think about it?
Just a hydrogen pair.
That's right. The hydrogen is getting added. Okay, great. So, okay, I think that's all we had here. And then maybe let's just go to the formal chart really fast. Okay, hold on. Actually, might have a few answers here. Might have to just remove them first.
Wait, is this from Klein? Like the problems itself?
Yes, they all are. Yeah, yeah.
Yeah, they're kind of familiar. But the problem with the Klein is like they have the problems, but there's no like solutions. Like it's just like
In the
they have
textbook?
problems.
Really?
Yeah.
Let me
So
see.
I wasn't gonna do any of the problems until we like met for the classes because like
Yeah,
it
yeah.
kind of yeah.
Wait, hold on. So I think well, because I've been teaching using Client for some time now. So Client, where is it? Let me just see really fast. I think they had some answers for sure. Let me see at the end of it. Where is my
Okay.
yeah, let me just double check really fast. Because I thought at the end of the towards the end of the textbook, yeah, they do, right? Yeah, they have all the answers actually.
Is it at the end?
It's yeah, at the end, yes.
Okay. Wait,
Yeah.
I have the fourth edition. Is that sufficient enough?
So for me,
Or
it says answer key, and I think let me look at my edition. My edition is second edition, but I'm pretty sure like it'll have
it
uh
doesn't matter, right?
yeah, it shouldn't matter. I am pretty sure it should have answers
Okay.
too.
Okay. And mine goes up to chapter 27, synthetic polymers. Are we gonna cover up to that, or is there more?
Um, chapter 27.
Yeah.
Okay. I do. So in the second edition, actually, they do. Maybe I'm gonna figure out if I can get the fourth edition because I have like only 13 chapters. Um,
Oh,
but
mine has 27.
27 chapters.
It covers OCHEM 1 and OCHEM 2.
Oh, that's why. Because like the one that I have only has OCHEM 1, and then the other one, I have another one which has OCHEM 2
Oh,
then, right? Probably that's why.
okay. Yeah. Because my school, like my teacher covers until half of OCHEM 2. So,
Oh, okay.
yeah.
Okay.
Yeah.
Yeah, maybe we can talk about the synthesis part when we get there. The
Yeah.
polymeric
Okay.
synthesis, right? Yeah. Okay.
Yeah. Okay.
So, well, do you remember how to get the formal charges?
Formal
And
charge.
so, okay,
Yeah.
so for each of the following structures, draw in all the lone pairs. So I think, yeah, it's like the opposite. The formal charges is given to us. We have to think about how many um, lone pair of electrons, if any, are present on
Yeah.
the respective atoms which have the charge. So on this carbon,
Okay.
which actually has the negative charge, is there a lone pair of electron here or not? And how would we
Yeah.
go about that?
So formal charge is -1. So
Yeah.
carbon has 4 valence electrons and it
That's
has
right.
3 bonds right now. So it has
Yes.
1 missing lone pair.
Yes. Oh, right. Perfect. So yes. So there is a lone pair here. Because in total it should have 5, right? 5 valence electrons. So then it has 1, 2, 3 shared in the 3 bonds, and then 4 and 5. All right, great. What about 1.61?
+1 charge for 3. It has 1 extra because it has a positive charge.
What do you
Wait,
mean has
no,
one
no.
extra?
No, it's missing 2 actually, my bad. Because formal charge is +1. 4. Three effective bond. It doesn't have any missing lone pairs.
That's correct. Yes, +1. But yeah, okay. So it means that, well, it's supposed to have 4 valence electrons, +1 meaning it has lost 1 electron. So then it should actually only have 3 electrons. It does have 3 electrons. So there is no there is no lone pair. And so, but does it have an octet though?
No.
That's right.
It only has 3 bonds.
Yeah, exactly. So
Wait.
carbon with the positive charge is electron deficient. It doesn't have an octet.
Yeah. Okay.
Yeah. Okay. What about 1.62? Does that have a lone pair?
Yeah, it has 2 lone pairs.
1,
Right.
2, 3.
Wait.
Um,
4 bonds. 3.
how come 2 though?
Wait, no, it has one lone pair and 2. Yeah, 1 pair. My bad.
One pair. Yes, that's right. And how we know that is because it's supposed to have 4, right? Valence electrons of carbon is 4. With the negative charge, it'll be 5 in total. So then we see the electrons of carbon are 1, 2, 3. These are the electrons of carbon. So then to have 5, then it will just have 1 lone pair.
Yeah.
Right. Okay. What about, so let's move on from carbon to, let's say, nitrogen with a negative charge.
Okay. So nitrogen has 5 valence electrons.
There's no much.
This one has 2. 2 lone pairs.
That's right, 2 lone pairs. Okay, what about the, let's say, 1.65 nitrogen with the positive charge?
Nitrogen with a positive charge. Okay, so 1, 2, 3, 4. It has 0 lone pairs. It has a full octet.
Perfect, great. What about 1.68 an oxygen with a positive charge?
1, 2, 3. 6 minus 3. Oh, it has 1 lone pair.
That's correct. It has 1 lone pair. Perfect. Okay, what about oxygen with a negative charge, 1.66?
So, well, I mean, to have a full octet needs, yeah. So 6 minus 1 lone pair, 5. So then it has two lone pairs. Oh wait, three lone pairs to get a negative charge.
Three
And
lone
to
pairs.
reach an octet too.
1, 2,
Yeah.
3, 4. 1, 2, 3, 4, 5, 6, 7. Yeah, that's right. Because oxygen has 6 valence electron. Yeah, that's right. Okay, good. Perfect.
Yeah.
Now let's do figuring out the 4 mole charge on the heteroatom, meaning oxygen or nitrogen, right? So let's do
Yeah.
1.35 and then we'll do 1.36 and 1.39 and maybe 1.38 as well. Okay, 1.35. The 4 mole charge on oxygen.
Positive 1.
Perfect. 4 mole charge on nitrogen in 1.36.
5 minus 4, so 1 minus 2, negative 1.
1, 2, 3, 4, 5, 6, 7, 8. Yeah. 1, 2, 3, 4, 5, 6. Yeah, perfect. Okay, what about 1.38?
Positive 1.
Positive 1.
Wait, oh, you have to count. Oh, yeah, my bad. So if it did not have 4 bonds, then you have to account for the lone pairs which aren't drawn.
Right.
Yeah.
Yeah, so they're given to you, right? They have drawn out the lone pairs.
Yeah,
So you don't have to
I remember
correct them.
having this one like test question where like the teacher didn't draw it, and
Oh,
like
she
I got
unexpected
it
you?
wrong. Yeah.
Oh, that
Yeah.
that's tricky. That's tricky business.
Yeah.
Yeah. Okay. About 1.39.
Six minus 6, 0, so negative 1.
That's right. Okay, perfect.
Okay.
Now, so let's do, what is it? Oh, same thing. Oh, so I think that's all we have for formal charge. So we can even move on to the resonance, right? And
Yeah, this I had some trouble with when we
okay, nice.
did it together.
Okay,
Yeah.
good. So for resonance, right? So we have to like look at 2 rules that are more important. So rule number 1 is that never exceed an octet. Never exceed an octet when moving electrons, and never exceed an octet. And the second rule is, what is it called? Don't break the single bond. You cannot break a single bond.
Yeah,
you can break a double bond.
Around double bonds.
Yeah, you can break the double bond, right? You can move the double bond, but you cannot move the single bond. So while these questions are kind of easier, I think I like that because they're taking us to the resonance structure. They're not asking you to write the resonance structure, but the question really is, if they moved this double bond from here to over this carbon, right? Then can they even do that to create a resonance structure? So the question is this movement of electron even possible when we are writing the resonance structure? So they're really taking it step by step, right? So okay. So let's think about this for 2.2. Can they actually do that? Is this
no,
the correct?
nitrogen has an octet already.
Exactly, that's right.
But don't we like expanded octets are
yes, so you can have expanded octets, but for like the 3rd period, right? Not the
for nitrogen doesn't have a d orbital, so
exactly.
it can't have,
That's right. That's right, exactly. So then if we even draw the structure after like the movement of arrows, it will actually look like this.
Yeah, and that's not.
Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nitrogen cannot really have 10 electrons, so this is not possible. No. What about 2.
The reason why we can move double bonds, not single bonds, is because pi orbitals can overlap and move, but sigma, like the sigma bonds can't.
Right, exactly. Sigma bonds are really strong bonds, and right, you cannot really break them. It takes they're very strong, right? So it takes a lot of energy to break a single bond, and when we think about double bonds, we're not really breaking it, we're just changing the location of it, right? But when we not change the location of a single bond, because that will involve like breaking it.
Okay, yeah.
That's why.
So
So for 2.3 now, if you think about it, this is actually more like a what kind of yeah, so is this possible? Can we do this movement of electrons to create the resonance structure?
yeah,
Yeah, exactly. And if we do that, how would it look like? It would actually look like this. So oxygen will actually get a an extra
negative
lone
charge.
pair, right? That's right. So with an
Yeah,
extra lone pair, it'll be a negative charge. And this carbon over here will now be electron deficient, so we can have a positive charge over here.
yeah, but in reality, like this resonance structure isn't actually
Yeah,
like valid,
it's
right?
right. So okay, so this is what, so you will write this as a resonance structure, but it's an unstable resonance structure.
Okay, but like you know how in Gen Chem, like sometimes the questions would ask you like draw a resonance structure for this, and we had to like, I mean, based off the formal charge, like pick the best one. Like,
Yes,
do we
yeah.
have to do that in OChem still,
Yes,
or no?
yes, right. You have to. And
Okay,
then there are all the different rules that you will use to think about which one is a more stable
yeah,
structure.
we learned about that too. Yeah,
Exactly. So then amongst
the
this structure
yeah,
and this structure, this is a more stable structure just because it's neutral, but then this one is
yeah,
charged, so that's not very stable. So it's less contributing or less stable to the overall structure. But yeah, the molecule can exist more like a positive and a negative charge like that. Yes. And it's a possible
yeah,
resonance structure too, because we're not exceeding an octet for oxygen, right? It still has like 1, 2, 3, 4, 5, 6, 7, 8 electrons in it. Carbon is electron deficient, which is fine. 1, 2, 3, 4, 5, 6. We're not really exceeding 8 electrons, but actually this is electron deficient. And part of the reason is that it is unstable because one of the atom actually doesn't even have an octet. So that's also a rule that when you have even multiple charged structures, then the structure which actually does not have an octet is the less stable structure compared to other structures which actually have octets. So we'll get to the rules. Okay.
yeah.
So what about 2.4? Is that a possible structure?
No, the carbon already has 4 bonds.
That's right. Yeah, because when we do that, and then so we're moving it to that carbon, so it'll look like this. And then now this carbon literally is forming, this carbon is
5
literally
bonds.
forming, right? 1, 2,
Yeah.
3, 4, 5. So that's not possible. What about the next one?
Uh, no, the oxygen can't have expanded octet.
It cannot.
And
Right. That's correct. It cannot
yeah,
have an expanded octet. It already has 8 electrons. So same problem. We'll get into the same problem. So we're adding more electrons. And again, to the single bond, especially if you're adding electrons, you have to remove the electrons. And when we're not moving electrons away, then that's definitely a problem. Right.
yeah,
So 1, 2, 3, 4. And then there'll be a positive here if I create the structure. So this is an unstable structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. What
yeah.
about the next
Okay.
one? Well, actually, yeah. Yeah, let's just do 2.6 as well, because the
Uh, yeah, this one should be fine. We're just taking the lone pair and making it. Oh wait.
yeah, okay. So if we think about it, we'll get this over here. Got the hydrogen here, and then we've got a lone pair.
But then the carbon will lose a hydrogen, right?
Right, exactly. And so, and that is a single
Okay.
bond. So we cannot just really move or like break single bonds. They exist just like that.
So that's not possible.
Yeah, so that's incorrect actually. Movement of that electrons
Okay.
is not possible.
Yeah, okay.
What about the next one, 2.7?
Oh, yeah, I think we covered this one. Yeah, yeah, you can. And then one side will just be positive and the one side will be negative.
Okay, so it'll look like this. So we got this, and this is a positive. Okay, but check this out though. This carbon already has two hydrogens, actually, if you think about it, right? Because it already has two hydrogens here.
Oh, yeah, okay.
Mm. So it's not really possible, actually.
Yeah. Oh, yeah. And then 2.8. No.
Yeah, exactly, because that's
Um,
just moving the single bond, not possible.
yeah.
2.9.
No, again.
That's right. Because again, moving the single
Wait,
bond, just that's not possible. Because like we are
yeah,
literally breaking that bond to form a double bond.
yeah. And then the last one, mm,
Yes, so you said what? Yes,
yeah, yeah, it should be because there's no hydrogens attached to the carbon because it has a triple bond, so
that's right.
it's
Yes.
fine.
Yeah. And when we do that, the nitrogen will get what will you have
No,
charges?
negative.
Right, exactly. Because we're
Oh,
creating an extra lone pair of electron there.
yeah. And then carbon will have a positive charge.
That's right.
Yeah.
Okay, perfect. Yeah, so that's possible. What about 2.11?
Uh, no, the carbon has hydrogen bonds, so yeah,
Which one are you looking at? 2.11, right?
yeah. The carbon has three hydrogen bonds, and if you take the triple bond and make it a double bond with the carbon, it removes one of the hydrogens, which cannot happen.
So we are
Wait,
moving the electron from the triple bond and ending up at the nitrogen as like a lone pair.
oh, lone pair. Okay, then it's fine actually. Wait,
So then that will give like this nitrogen a positive charge.
yeah, and then the other nitrogen will have a negative, no, neutral charge because it's already
Right. Yeah,
positive.
because there actually we're adding a lone pair of electron here, right?
Yeah.
Yeah.
Okay. Yeah.
So yeah, so is this structure possible? Yeah, there's no problem with that because uh this nitrogen has an octet. This doesn't, but 1, 2, 3, 4, 5, 6,
Yeah.
right? Yeah, but there's positive charge because of that. So yes, um, this is a possible resonance structure. And if we really think about it, do we have one structure that's more stable than the other structure? Not really, because there's a positive charge on this one and there's a positive charge on this one too.
Yeah.
They both are positive. Oh wait, 1, 2, 3, 4, 5, 6, 7. Yeah, there is actually. There is one more stable because does this nitrogen have an octet?
No.
Yeah, but then everything here has an octet.
Okay. So then,
4, 5, 6, 7, 8. Yeah. And then 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So this actually is a more stable structure compared to this one. Okay. What about
uh,
12? Next one.
no. Uh,
Yes. Mm-hmm.
yeah, yeah. Hydrogen bonds.
Yeah, there are two hydrogens here, and then we're literally creating the fifth bond, which is not possible.
Yeah. So wait, does this just come with practice, like being
Yeah.
able to
Yes.
do it quickly?
Right. Because like when you expand out, like when you're able to see every bond, then you'll just know it's possible or not, right?
Yeah. Okay.
Yeah. With the positive
It's like
charge.
I can do it, but it's like taking me like some time to like
Because you have to
go
like
through it.
look at every bond in the bond line structure. I think that's the only reason. Because like I think the only one time you got this wrong was because you didn't realize there are two hydrogens actually present here, right?
Yeah.
Yeah. I think
Yeah.
that's the only one thing that you need some practice with.
Yeah.
Okay. All right. So in this one now, they want you to draw out the curved arrows that will get us from one drawing to the other resonance structure drawing, which is also, I think, pretty simple. We can even do it really fast. So, well, going from a neutral to a neutral, right? 2.14. So how would that actually look like?
Each double bond is just going one to the left, or like
Right.
one
Okay.
one counterclockwise.
Oh, okay, so we're going from left to right. If we go from really from left to right and not from like here to here, right? So it's more
Yeah.
clockwise then.
Okay, so you're saying like it goes like this way, or
Right, so this double bond which is over here is going this way, right? So then meaning this double bond moves over here. So then it
oh,
goes here.
okay. So we don't like we always go clockwise.
Well,
And
they just want you to go from this structure to that structure, not necessarily clockwise or anti-clockwise. They will
okay,
like how we did here, right? Just draw the first structure, then draw the arrow, whatever arrow is representing. You will draw the second structure, which is the result of the movement of electrons represented by this arrow,
okay, yeah, okay,
right? So whatever arrow is showing
yeah,
us is what the next structure will be written as. So then
yeah.
going from here to here, we are saying, okay, these electrons are going here. Then these ones are moving over here because we see the new double bond here. And then these electrons are moving over here. And then these are two resonance forms, which also means the same way or a different way to represent the same molecule, or the different bonding to represent the same molecule, meaning then that it can exist like this or like this in a resonance structure.
Yeah.
Okay. 2.15. How would the arrow look like? So we want to go from like this structure to this structure. How will the bonding environment look like?
The double bond is going up to the low
Yeah,
to the positive charge. Yeah.
there you go. Exactly. Just that, right? Just one movement of electron. What about 2.16?
Oh yeah, this one I've seen a lot. It's like really common. So basically the double bond just goes to the left, and then the positive charge ends up, yeah.
Yeah. On
What are they call this, like allyl carbonization or something?
yeah, carbocation, allyl
Yeah.
carbocation.
Yeah. Okay. I've seen this somewhere.
Nice.
I
Yeah.
think in the textbook, yeah. Okay.
Yeah. Nice. Okay.
Uh
Okay, what about this one?
oh yeah, so the double bond at the top right is basically going to the right by one.
Yeah, exactly. That's right. Like that.
Yeah.
That's it, right?
Yeah.
Okay, what about 2.18?
Okay. This is an ion some sort. Uh yeah, it's just the movement of the double bond again. The double bond is going to the top now.
Yeah, so
And
how do we show it with the arrow?
the arrow is gonna start from the double bond onto the bottom right oxygen, and it's gonna go up to the single bond to the top oxygen.
So again, you're doing this, right? So what if we have to actually go from represent it at this structure? Okay, we can represent it at this structure like this. What about this structure on the left?
Yeah, that also works, right?
Right, but when we're writing the resonance structures, we're really going from the first to the second.
Yeah, yeah. I was talking about the bottom right double bond going up to the top.
Oh, I see. Oh, okay. Can you do that actually? Let's check. Can we actually do that?
No,
Yeah, because then oxygen will actually
no,
get more
yeah.
electrons, right? 1, 2,
So
3,
then
4, 5, 6, 7, 8, 9, 10. Yeah.
oh wait, is this a double? Are there two arrows? The the
This
negative
one?
charge goes to the, yeah.
Yes. So over to the right, is that what you're saying? The one that I drew?
Yeah, they're like like the only way the negative charge ends up at the top is if there's two arrows, right?
Yeah, exactly. Yes. Yeah. So when we have negatively charged structures, we use two arrows to represent them. When we have positively charged structures, we only usually need one arrow, to write the resonance structure, but when like all of these are positive, right? When you actually have the structure with negative charges, you will see a total of 2 arrows.
Okay, yeah. So it'll start from the top and it'll go to the single bond to form
Yeah.
the double bond.
Yes.
And then the then I'm pretty sure
Mm.
because then it's a double bond there. Um, oh, and then the double bond will then go to the
Yeah,
oxygen and then form
that's
the
right.
negative charge there.
That's
Yeah,
exactly
okay.
right. Yes, and it makes
Okay.
sense now because again, at this carbon, right, we are bringing in the electrons, and it's cool because the next bond is a double bond. You can always move electrons from the double bond. So when you bring in the electrons, we can bring out the electrons
Yeah,
to the oxygen as a negative.
maintain the octet as well. Yeah.
Yes, exactly, right. So same thing, bring in electrons, take out electrons as well. So,
Yeah.
okay.
Wait, because the carbon is in the center, right?
Yes,
Yeah.
exactly. Yeah.
So yeah, it has to have 4 bonds in total. Yeah. Okay, that makes sense.
Right. Yeah, exactly. So it already has 4, right? If it was all single
Yeah.
bond, then it would have been a problem. If it was all single, then there was a hydrogen here. That would have been a problem. Then you cannot really bring in the electrons because like we cannot really move any of the single bonds. But so the cool thing to kind of recognize here for resonance is when you have alternating double bonds, right? Then it's easy to draw out the resonance, meaning we can draw out a resonance for this structure because what we really see is a double, single, and a double. So these are alternating double bonds. So you can also alternate with the charges as well. So if you have double, single, and a negative, that also can give you a resonance structure. So even like again, if it is alternating or continuously alternating again with the double bond, so you can draw a resonance structure for that as well. So that's like double, single, negative, single, and double. So that's telling you you can draw out a resonance for that. And then if you only have this though, that's a problem because
There's
there's
hydrogens
nothing
attached.
there's
Yeah.
nothing alternating here. So that's a problem. But if
Yeah.
it's alternating with a positive charge, then that's great because then you have double, single, and positive, right? So that's even. Any kind of charge will help resonate in the resonance structure. So you
Yeah.
can have, so you need to
So,
have 3 of those possibilities for you to write the resonance structure.
but the first two, you're just like swapping them, right? Like
This one
you're like like you're just swapping the like what we just saw of for example
in the
2.18.
benzene, in the 2.18.
Oh yeah, or that one, yeah. Like you're just like all like swapping like the order of like where the double bond is, right?
Right, exactly. And also, you can also write them as charges too, right? Because every double bond, well, think about this, double bond can actually be written as, so I can move the electrons in the double bond to the end carbon. So that would actually look like this. So you would actually get a negative here and a positive here. So you can write a double bond with a charge of a positive and a negative, right? Just think about both electrons situated on one carbon atom. So one of them becomes positive. Then we've got the situation again, double, single, positive. So then we can resonate just with this. So we can create another structure, which will actually be a resonance structure. So these electrons moved over there. So then we've got another resonance structure. We've got a positive here, double here, and a negative here. So again, for a linear structure, right, this is a neutral structure. There's no other neutral structure possible for a linear structure. There's no other way I can rotate the bond so I can again get another neutral structure. But for benzene, right, because of its cyclic nature, you can have a neutral structure, another possible neutral structure, and then of course we can create a positive and a negative for every double bond and then resonate them. But think about how unstable those structures are compared to just like neutral structure of the benzene. So these are the major structures, but of course, if they said draw out 6 structures, you can draw them out. You can like write every double bond as a positive and negative, then you can just move the other double bond to create a different resonance structure and then move this double bond to create a different structure. So that's possible. But for linear structure, right, there is no way we can have another neutral structure. And if they say draw out resonance structures, so then you will actually draw out these kind of unstable structures.
Yeah. Okay.
All right. So then let's look at 2.19 and see if that, how would we draw the arrows to go from one structure to the other?
Uh, so like I noticed that the nitrogen is now having a negative charge,
Yes.
and the double bond has moved to where the negative charge is originally. So I'm thinking that the double bond is going to move one to the right, and the negative charge will move to the left.
Right. Oh, wait. You said it will move to the
Wait.
right? Oh, yeah. So you're doing that again, right? Is that the possible thing? And again, think about this, right? Because if you're removing the electron kind of from nitrogen, you're saying this double bond is going to be situated at this carbon, then this nitrogen should actually, we're kind of robbing that nitrogen
Oh
from
yeah,
electrons. So then
positive.
we're kind of going more towards positive charge. But that's not happening here. So
then yeah, it'll move to the nitrogen itself and give it a lone pair.
yes, exactly.
But
Right.
a double bond. Oh, the negative charge is a double bond, right? So
Yeah,
then the
exactly.
negative charge on that carbon will then just become a double bond.
Yes, exactly. So then like that.
Oh, because the carbon has an extra lone pair. Oh,
Yes,
okay.
exactly.
So we're moving the lone pair to make a bond.
Right. Yes, exactly. So maybe I should write the fourth, another possibility, right? Is this as well. So more like a lone pair of electron here, like that. So then we can also do this and a movement to create a resonance structure. And then with the negative charge, we'll do more like this to create a resonance structure.
Yeah, okay. That makes a lot more sense.
Right? Okay, perfect. Do we have more problems here? Oh, we do. Okay. All right. So I think now they want you to actually write the resonance structure instead of writing the arrows. So when the arrow moved like that, how will the resonance structure, the new resonance structure actually look like?
Can you zoom in a little bit more?
Yeah.
Okay, so first things first, the double bond is moving to the oxygen, so it's adding a lone pair. So that means the oxygen will be negative now because it has three lone pairs. Wait, no.
Yes.
Right now it has two lone pairs, yeah, and then it has three lone pairs, and it has one bond. So then it has a negative formal charge.
Yes.
Then the nitrogen already has a positive formal charge right now, but we're moving the double bond to the nitrogen to allow it to still have so it'll still have a positive charge because it now lost a bond and it gained a bond. So it's
so it's still the same. Yes.
Yeah.
That's correct.
Okay, and then let's go to the cyclic structure. So one of the double bonds is still there on the left side.
Yeah.
And now we just moved one double bond to there. So basically what's happening is that when the double bond moves, it's going to form a negative charge on the right side, and on the bottom side, it's going to leave a positive charge because we lost the.
Okay, so you're saying a negative here, a positive here? Okay.
Yeah.
What about this carbon?
Wait, no, like over there, like it has a negative there, and
Oh, negative here.
Oh wait, no, that one's positive because it lost the bond. My bad. Yeah, that one is positive.
Okay, so that's positive. Okay.
And then everything else is negative on the next one, and then positive on the bottom.
Okay, so if you read this arrow right, so this arrow is saying that there is a double bond here, and now this double bond is moving over to this single bond, which means that the location of the double bond is changing, which means that because you already see that there is a deficiency created here, so we can add a double bond here actually.
Okay.
And that will
Uh,
then, when that double bond moved from its position, then this carbon will actually be deficient now because the electrons are moved over to this position. So now that will actually just leave a positive charge. Although what you said was kind of close already, because you said positive and a negative, right? So
yeah,
it's almost like this negative and this positive can constitute actually a double bond. This is actually a double bond.
yeah. Okay. So for these sort of problems, do you recommend working with the cyclic structure first to like make sure
Um,
you account for like the charge
what do you
that you're
mean
losing?
cyclic structure?
Like, should I
Oh,
start
you're
from
saying
the
okay.
cyclic
Not
structure
really
first?
though. Not really. I mean, not
Okay.
necessarily. I don't think it should be. It should matter if you start here versus if
Okay.
you start here. Yeah.
Okay.
Especially because yeah, it's given to you, right? But hold on.
Yeah. So the
There's
double
something
bond.
wrong. Well, hold on, let me think about it. Is there, yeah, there's something wrong here. Yeah, what's wrong? So this is incomplete because conservation of charges, we have to maintain the total charge in the structure. And the total charge over here is zero, one positive, one negative. But in this structure, there is a total positive plus one. So we're missing something.
The oxygen still has a minus charge.
Right. So yeah,
Yeah.
that's why. Okay.
Yeah.
Okay.
Uh,
Next one. I think the next one's easier.
uh, okay, yeah, so let's just start from the minus charge. The minus charge is leaving the carbon because it has extra lone pair and it's gonna form a double bond.
Mm.
Um, I think that's the oh, this is just a mirror image, right? Because the double bond will then go to the carbon
Yeah,
on the
yes,
left end.
yes.
And
It will be a mirror image here, right? Yeah.
yeah,
So then we'll get like a negative charge here and a double bond here. And that's what you said, right?
yeah.
Okay.
Okay.
Okay. What about the next one?
Okay. I guess we can start from the bottom oxygen.
Sure.
So the lone pair is gonna form a double bond.
Yeah,
Um, and because of that, we need to maintain four bonds in the central carbon, so the double bond will get lost from the top oxygen and it'll form a lone pair.
that's
And the
right.
oxygen will now have a negative charge, and to maintain charge, the bottom oxygen now will have a positive charge because the original structure was neutral.
That's right. Right. So then we've got one,
Yeah,
two, three, four, and a positive charge. And then you've got a negative charge over here. Yep. Great.
yeah, okay.
Okay. Let's do 2.24. But kind of pretty
Um,
simple now. But I think because
yeah,
we've done those. Yeah.
yeah, same story. So the negative charge will form a double bond,
Mm.
and then again the double bond will move up to nitrogen, and nitrogen will have
Yeah.
an additional lone pair.
Yeah.
And now the charge is so nitrogen will now have a negative charge
That's
to
right.
maintain charge pretty much.
Yeah.
And then
Exactly.
the bottom is just neutral now.
Yeah, exactly. And then there's conservation of charge. So it's overall negative, it's
Yeah.
overall negative. So which is perfect. Okay.
Yeah.
What about the next one?
Okay. Uh wait, it looks like the arrows that they draw is like showing like cause and effect. Like
What do you
it's
mean?
like
Yeah, like it's telling you what to do. It's already telling you where to
well,
move
yeah,
the electrons.
it's like kind of telling you like the first step and then what happens because of the first step and then like keeps going.
That's right. Yeah, that's exactly right. Yeah.
Okay, yeah. So then you have to start from the top. So then we're losing
Okay.
a lone pair. We're to form a double bond.
Yeah.
So and we're because we're losing a lone pair, the oxygen now has a positive charge.
Mm. Yeah. Okay. Hold on.
Okay,
So
so
we have,
that's
yeah.
fine.
Okay. Perfect. Yeah.
Okay. So now that we've moved the lone pair from double
Mm.
bond,
Yeah.
okay, we countercharge. Okay, so then we can move on to the next part. So that oxygen now has five bonds. So then we need to not oxygen, carbon has five bonds. So we need to lose the double bond.
Yeah.
So we move the double bond to the next carbon to the right.
Mm.
Okay, so then what happens to the charge? So,
Yeah.
uh, what does happen to the
Think about just what's happening in the next arrow, right? So, okay, there is one hydrogen here. So let's add the atoms to kind of make sure. Look for formal charge then, right? At that carbon, look for, is there any missing valence electrons? So then 1, 2, 3, 4. Carbon has 4 valence electrons. It's using the four of its valence electrons,
Yeah,
so it doesn't have extra electrons
so
really. So formal charge
this
here is
is
0, right?
yeah,
And
that's
then
what I thought. Yeah,
there's a hydrogen here too, so there's a hydrogen here as well.
yeah, and then the bond is just gonna get moved. So,
Yeah, exactly. So we've got
but there
them.
has to be a negative charge somewhere to
Right,
maintain
and
bond.
then
Maybe
look for what's the next arrow doing. So this arrow represents the movement of this double bond over to this bond. But then think about what this bond is doing, right? This arrow is actually moving the electron in this bond over to the carbon.
you're actually looking where the arrow's pointing. Okay, yeah.
Yeah,
So
exactly.
since it's gonna add a lone pair to that carbon, and
Yes,
that's where we
exactly.
get the negative charge.
Right,
Okay.
exactly. So that's where we're getting the lone pair and that extra negative charge.
Okay, yeah, actually that's a good point. Like, because some of them are actually pointing to a bond, and then some of them are
Yes,
pointing to the node. Okay.
exactly. That's right. Yes. The ones that are pointing to the atom are giving you a negative charge, and then other ones are just going from bond to bond,
Yeah. Okay.
right? So, and then, well, this
But
is a correct.
there's one more bond,
Yes,
double
that's
bond.
right. Yeah. So that doesn't change because it's same here,
Yeah.
right?
Okay.
So then
Yeah.
we've got overall neutral to
I think I need to work with the cyclic, like
structures.
again
Yeah.
mapping out with the hydrogens. Yeah.
Whoops. Okay, I've got a few structures here too. So yeah, you've got some problems here. And I wonder if like the second and the fourth edition are like any different. So you might just like check if in your textbook you've got more problems that are different.
Yeah. So
Well,
I
actually,
like I haven't.
there are a lot of them here. Yeah, I guess 46
Yeah.
problems.
So
So
like right
you have
now
some more
like
practice
I've
here that you can get.
yeah. So I haven't been like reading the like Sundal like last week, but like I was just reading like chapters 1, 2, and 3. So like review of Gen Chem, molecular representation of online drawing. I started with acid and bases, and like is that enough? Like this week at least?
Yeah, I think for sure.
Yeah,
Because
okay.
tomorrow
Yeah. And
we'll
then
get
yeah,
to
I'll
like
just like review.
we'll get some more practice for resonance structures tomorrow. And then if we have the time, then we'll probably
Yeah.
start off with the acid bases. Um, right. But I think
Okay.
resonance is something that usually takes a little bit for most students. So
Yeah.
because these are still the simpler ones, right? Because then they'll ask you to draw out like 5 structures from one structure, keep moving the electrons. So we'll get some more practice done for that. And then using the rules to determine which one is the stable resonance structure. And we will do that too. Yeah, and then if you have a little bit of time, we'll do acid
Yeah.
base. So I think you should be fine if you've done that reading.
Okay. Yeah.
Yeah.
Yeah. And then like during the week, I'll just read whatever we're due next week, I guess. Yeah.
Yeah, exactly. And just like get some more practice of the problems that I'll be sending.
Yeah.
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 Yeah, I think, yeah, that's more
Okay.
important as well. Yeah. So, okay. All right. So, yeah,
All right.
I think, yeah. So tomorrow we'll start up here, right, with the resonance structures.
Yeah.
I'll send you the notes
Okay.
that I created. And same time
Yeah.
tomorrow, 12 EST, which is, I think, 11
Yeah.
for you. Okay.
Yeah. And then the problems are just the ones that you put in Google Drive, right?
Yeah,
Like,
exactly.
are there any like, are there anything you want me to do like today before we meet tomorrow?
Yeah,
Or
like yes, for sure. So I think we just we went over some of the formal charges. Probably I left like a few of them. You can like finish those off.
okay.
I'll send you those
Yeah.
notes so then you'll know which ones are left over. And there are the other ones like the resonance structures. I think we did until like 28 or 26, and then there are like
Okay.
total of 39 problems. So you have like no, actually more, 46. So you have like
Okay.
about 20 problems there. So yes, get some
Okay. Yeah.
practice for resonance too. That will be really helpful
Yeah.
for tomorrow.
Okay.
Right?
Okay. See you.
Sounds
Yeah.
good. I'll see you tomorrow then. Okay.
Okay, bye.
Bye now.